Chapter 5 will deal with the analysis of proteins. There are two major techniques to separate proteins. One is gel electrophoresis and the other one is high-performance liquid chromatography, which you've already heard about. As mentioned before, proteins are very important new class of pharmaceuticals, so-called biopharmaceuticals. Proteins as pharmaceuticals have been around for a long time, think of insulin, but only due to the development of recombinant DNA technology was it possible to make proteins at will. The recent class of monoclonal antibodies, which has its diversity based on the various binding sites that antibodies have and can be engineered into antibodies, is a great success in biopharmaceutical development, and some of the mostly sold pharmaceuticals in the world are monoclonal antibodies. There are two principal means of separating proteins by gel electrophoresis. First, by polyacrylamide gel electrophoresis in the presence of the detergent sodium Dodecylsulfate, widely known as SDS-Page. And second, by isoelectric focusing in a polyacrylamide gel using immobilized ampholytes. You will perform SDS-Page and IAF during the practical course of Pharmaceutical Analysis C. While SDS polyacrylamide gels can be bought off the shelf nowadays, it is good to know how they are prepared and what they contain. Here you see somebody that's prepared polyacrylamide gel. It's essentially initially a liquid that is poured between two glass plates of about 1 millimeter apart, then let to polymerize. This generates some kind of a wobbly gel-like structure, which we will hear a little bit more. The important thing in SDS polyacrylamide gels is that they contain pores of a certain size. Some proteins are small enough to migrate through the pores, while others have difficulties because they are bigger than the pores. This leads to separation of proteins according to size. You can also see that it takes some caution to run SDS polyacrylamide gels. Especially, you should not touch materials with your hands, because your hands contain proteins on the surface, especially keratins. If you touch the gel or samples or pipette tips with your hands, there's a high chance that you will contaminate your sample with keratins, and that later, when you want to identify the proteins, it will be difficult because most of your hits will be due to the contaminating keratins. Here is an overview of the chemical structure of polyacrylamide. It's composed of two monomers, acrylamide and N-primed methylene bisacrylamide. Look at the structures on the upper left and upper right. Acrylamide is an amide with an alpha-beta unsaturated double bond. This double bond can be activated by radicals and thus initiate the polymerization as the generated radical attacks another double bond. Bisacrylamide, as it is often called abbreviated, has two of such groups that are linked together with a CH2 group. This means that polymerizing bisacrylamide into a polyacrylamide gel leads to cross-links between the growing polyacrylamide chains. Were there no bisacrylamide, polyacrylamide would be something like honey. Thanks to the bisacrylamide, it's cross-linked and has somewhat more rigid structure. You can see at the bottom of the gel what a polyacrylamide gel looks like. It's actually a polyamide, just like nylon, cross-linked with bisacrylamide. You can imagine if you add a lot of bisacrylamide, you will get a lot of cross-links or bridges as shown here. That means you get a lot of small pores. If you use little bisacrylamide, you get fewer bridges and the pores will be larger. You will also see that on the consistency of the gel. A gel with a lot of bisacrylamide is rather rigid and sometimes brittle, while if you have a gel with very little bisacrylamide, it's somewhat floppy and soft. The concentration of acrylamide also contributes to the consistency of the gel. A high concentration of acrylamide leads to many chains that are cross-linked and smaller pores. The gel will appear more dense. If you use little acrylamide, meaning something like 5%, and a lot is something like 15 or 20%, then you will have a very floppy gel with also large pores. It is thus the combination of the concentration of acrylamide and the percentage of bisacrylamide relative to acrylamide that determines the overall gel structure and also the pore size. In the end, it determines which proteins can be separated and which proteins are too big or too small to be separated. Indeed, this is shown in this plot. Look at the x-axis. Here you see the migration distance of different proteins from 0 to 16 centimeters. This is the length of the gel essentially. On the y-axis you see a logarithmic scale of the molecular weight of the proteins times 1000. Now we have three different gels. We have a gel with 5% acrylamide, assuming consistent percentages of bisacrylamide here. This is a very floppy gel with large pores. It's ideally suited to separate very large proteins from above 200,000 Dalton to about 60,000 Dalton. However, it's unsuitable to separate small proteins. All the proteins from 60,000 down to 30,000 all migrate with the buffer front. That means they all come out at the same place and are not separated. If I want to separate these proteins a little better, I can increase the concentration of acrylamide. Here we have 10% acrylamide gel in the middle. As you can see on the left, separation for the very big proteins kind of deteriorates. They are closer together. In the middle, the separation is ideal. You have a linear range from about 70,000 Dalton to about 20,000 Dalton. The very small proteins below 20,000 Dalton can no longer be separated. Finally, we can use a 15% acrylamide gel, high density and small pores. The large proteins have trouble entering these gels, so they're almost all at the beginning of the gel between 0 and 2 centimeters. Only as proteins approach the molecular weight of 40,000 Dalton, you can see a separation that stretches to about 15,000 Dalton. Proteins below 15,000 Dalton are a little bit separated, but not very well. But separation reaches down all the way to 3,000 Dalton. Indeed, there are other buffer systems which also contribute to the separation of smaller proteins. This goes beyond the scope of this course, but it's very important also to remember that the migration of the buffer ions also plays an important role in the separation of the proteins in polyacrylamide gels. Ferguson looked at the relationship between the logarithm of the electrophoretic mobility on the y-axis and the percentage T, which is composed of the percentages of acrylamide and bisacrylamide. Please look at the reader for the formula for T. Small protein migrates fast. Remember, we are talking about the negative logarithm here, minus 4.2 for example. So it's on the top. But what is important, there's a linear relationship between log mu E and percentage T. In the middle you have two middle-sized proteins, and at the bottom, with the slowest mobility, a big protein. Mobility is mainly affected by the pores and how well a protein can worm its way through the pores essentially. A very striking feature of the Ferguson plot is that if you extrapolate to a situation where there is no polyacrylamide at all, 0% T, that means free flow electrophoresis, all proteins would migrate at the same speed or have the same electrophoretic mobility. This is strange, as you might think that a bigger protein still has more hydrodynamic drag and would move more slowly than a small protein. However, we have to remember we're working in the presence of SDS, sodium Dodecylsulfate, a surfactant that confers negative charges to all the proteins. In fact, it coats the proteins with negative charges, the hydrophobic part of SDS interacting with the hydrophobic parts of the proteins, and the hydrophilic head groups, the sulfate groups, into solution. This means that bigger proteins will acquire more SDS than smaller proteins, so that the overall surface charge density of negative charges will be the same. And this results in the same electrophoretic mobility for all proteins, small or big, because a small protein carries less charge and a big protein carries more charge. At the end of the day, they all have the same charge density, which is the determinant for the electrophoretic mobility. We talked quite a bit about sodium dodecylsulfate, SDS, and its importance to confer equal charge density and equal electrophoretic mobility on all proteins in the absence of pores. So let's take a look at the molecular properties of SDS. It's a fairly simple molecule, composed of a hydrophilic sulfate head group and a hydrophobic C12CH2 carbon tail. It's usually provided as the sodium salt. As a surfactant, or sometimes called detergent, SDS has a critical micellar concentration, a CMC. This is about 7 to 10 millimolar at 20 to 25 degrees. What does this mean? At a concentration of 7 to 10 millimolar, which is by the way also dependent on the ionic strength of the solution, SDS molecules will aggregate together to form micelles. At 10 millimolar, this is 50% of SDS will be in micelles, and the other 50% will be monomeric in solution. A micelle of SDS has an aggregation number on the average of 62 molecules per micelle, so it's actually fairly big. With a molecular weight of 288.5 gram per mole and an aggregation number of 62, this gives a micelle an approximate molecular weight of a small protein of 18 kilodalton. So you can see, as proteins are incorporated into these negatively charged micelles or coated by SDS, as it may, then they acquire a lot of negative charge, and this leads to a constant charge density. When you're finished with your gel, and as you've seen in the little movie if you looked at the link, you'll see only the migrating dye. These are simply dyes added to your solution to show you how far electrophoresis has progressed. But you do not see the proteins. Proteins are not visible to the naked eye unless they are colored like a few are, like hemoglobin. But most proteins only absorb UV light. So you have to stain them, or in other words, you have to make them visible in the gel. A very popular type of stains are the Coomassie blue stains. They originally were designed as textile stains to stain wool. Here's an example of Coomassie blue R250. There are many Coomassie blues. Now wool is made of proteins, so it was a logical conclusion to use Coomassie dyes to stain proteins in gels. You can see that Coomassie dyes are a much more complicated structure than SDS. However, they contain some similarities. They have large hydrophobic part of conjugated aromatic rings, and they have sulfonate groups resembling the head groups of SDS. So Coomassie blue associates with the SDS protein complexes and binds to them. There are 3 steps to making proteins visible in a gel. First you stain with Coomassie blue, then all your gel will be blue. You remove the stain and you destain, for example with an acetic acid methanol solution. This will destain or remove the Coomassie blue from all the areas where there are no proteins. However, as it binds to the protein SDS complexes, Coomassie blue will stay where the proteins are and show them as bands on the gel. Finally, you can conserve your gel, either by putting it and sealing it in a plastic bag, or by drying it, or if you do not need the actual gel anymore, you can scan it and take a photo. This is a simple polyacrylamide gel, an SDS page. We see bovine serum albumin samples on the left and molecular weight standards on the right. Every SDS page gel should contain one lane with standards, so you can assign the approximative molecular weight of your molecules. You see the standards here range from 97,400 to 21,500. I believe this was a 12% acrylamide gel. Interestingly, the bovine serum albumin does not appear pure. The main band is at the expected molecular weight of about 60,000 Dalton. However, there are bands at about 100 or 120,000 and above, and there is even protein aggregated in the pockets between the stacking gel, which is a gel of low acrylamide concentration, and the separating gel. This is due to aggregation of bovine serum albumin. This could have happened already in the commercial sample or during sample preparation, which usually comprises heating the samples in sample buffer, means an SDS containing buffer prior to the gel, to assure complete denaturation and formation of the protein SDS complexes. Let's move on to the other important technique of electrophoretic separation of proteins. It's called isoelectric focusing, or abbreviated IEF. IEF comprises focusing proteins in a pH gradient. We'll discuss why do proteins focus in a pH gradient and the so-called isoelectric point of a protein. And we will also discuss how to generate a pH gradient in a polyacrylamide gel. But let's first address the question, why do proteins focus in a pH gradient? That's because proteins contain charged amino acids, which have a charge dependent on the pH. Remember maybe the earlier chapter on solid phase extraction and liquid-liquid extraction for drugs. In the same way, proteins contain basic and acidic group, each of them with their own dissociation constant. So dependent on the pH, proteins will contain positive or negative charge or will be overall neutral. Here is one negatively charged acidic amino acid, aspartic acid. You can see the two carboxylic acid groups with their pKs and the amino group. Overall, aspartic acid has an isoelectric point of 2.77. That means at pH 2.77 it is overall neutral. It contains the same number of positive and negative charges. The second acidic amino acid is glutamic acid. It's very similar to aspartic acid, just has one more CH2 group. This affects slightly the pK values of the carboxylic acid groups. It's slightly less acidic than aspartic acid with a pI of 3.22. There are also positively charged amino acids in proteins. One is lysine, shown on the left. It has the carboxylic acid and the amino group, like all amino acids, and in the side chain it has another primary amino group with a pK of 10.53. This gives lysine an overall isoelectric point of 9.74. Another amino acid that is basic is arginine. It has the guanidinium group in the side chain with a pK of 12.48. This gives it a pI, an isoelectric point of 10.76. And finally, an interesting amino acid, histidine. Histidine has an imidazole in its side chain with a pK of 6. That means histidine is partially charged and partially neutral at physiological pH. It has a pI of 7.59. So imagine a protein composed of a sequence of amino acids. As you may remember from earlier semesters, protein biosynthesis effectuated at the ribosomes, and one amino acid is connected to the next according to the code of the messenger RNA. That means a protein contains many negatively charged and many positively charged amino acids. These can be hundreds. Overall, this will confer many positive and many negative charges on proteins. The place where the number of negative charges is exactly equal to the number of positive charges is called the isoelectric point of the protein. It is this isoelectric point that the protein tries to reach in isoelectric focusing. Here is an example of the three-dimensional structure of a protein containing negatively charged, indicated in red, and positively charged, indicated in blue, amino acids. As you can see in this case, and this is true for most proteins, these amino acids are not just randomly distributed over the surface. There are red patches rich in negative charges, and there are blue patches where there are positively charged amino acids. We will come back to this when we talk about protein chromatography. In electrophoresis, you can now imagine if the red negatively charged amino acids exactly balance the number of blue positively charged amino acids, in an electric field there will be a force in the one direction to one electrode and an equal force in the electric field to the other electrode. As the force is by far not strong enough to rip the protein apart, the protein will simply stop moving because it's pulled from both ends with the same force. On the top of this slide, you'll see the principle why proteins focus in a pH gradient during isoelectric focusing. Imagine a protein at its isoelectric point, diffusing away from it, as it must because there is a concentration gradient. Going to the left, it will go to lower pH and acquire positive charge. Now the positive charge is more in number than the negative charge, so there will be a net electric force driving the protein back to its isoelectric point. As the protein diffuses to the right into the more basic region of the pH gradient, it will acquire more negative charge. So again, a net electric force will drive it back to its isoelectric point. This is a zoom of one place on the isoelectric focusing gel, which contains a pH gradient. You can see other bands because proteins have different isoelectric points dependent on their composition and the number of positively and negatively charged amino acids in their sequence. When you apply a strong electric field of a couple of thousand volts and a cathode and an anode, each protein will be forced to migrate towards its isoelectric point and to stay there. That's why it is a focusing technique with extremely high resolution. This is also shown in the graphic below. At the isoelectric point, the protein will stay at its place X, and if it moves away, it will experience an electric force that will drive it back to that place. Here is a schematic to illustrate how the charge of a protein changes with pH. Imagine you have an isoelectric focusing gel with a pH ranging from 1 to 14. This is usually not used in practice because no protein has an isoelectric point of 1 or 2 or 13 or 14. Generally the widest gradients that are used are 3 to 10. But anyway, for the illustration we can see that at very acidic pH the protein has a lot of positive charge, almost 40 charges. As the pH increases, the number of positive charges declines until it reaches 0 at about pH 7. As we go further to the basic side, the protein will acquire negative charge, up to a value of about 43. These numbers are dependent on the number of basic and acidic amino acids in this protein. You can see that the isoelectric point is about around pH 7 in this case. Actually, it's calculated to be 6.9. We should remember, however, that this isoelectric point is a pure calculation. It does not take the three-dimensional structure of the protein into account, nor does it take the clustering of charges into account as shown on one of the previous slides. However, such a calculation is quite useful. It's easily done and there's software for it. The isoelectric point, the calculated isoelectric point, is the sum of all the pKs of all the positively and negatively charged amino acids. or let's better say the dissociable groups in these amino acids, divided by their number. These are the dissociation constants of the ionizable groups in the protein. It's better described here than what I said. And N is the number of ionizable groups. Now let's address the question how to generate a pH gradient. We heard about SDS page gels. It was not obvious how do you make a pH gradient in a polyacrylamide gel. Obviously you need molecules that have themselves isoelectric points and that will focus in such a gel. These are called ampholytes. On the top here you see a typical ampholite molecule. It's kind of a small amino acid derivative with carboxylic acid and amino groups. Taken together, this ampholite will have a slightly basic isoelectric point because it has 3 amino groups and 2 carboxylic acid groups. In an electric field, it will migrate to its isoelectric point and stay there. If you have many ampholytes in a gel, they will overlap in their isoelectric points and they will generate a pH gradient. However, this pH gradient is not very stable. This was the old way of making it, but it does migrate due to the electroosmotic flow. The electroosmotic flow is due to the charged bilayer between the glass plates and the gel, or between the plastic backing and the gel, depending on what kind of gel it is. And then the pH gradient within a few hours will migrate out at the cathode end of the electrophoresis system. This means you cannot focus for a very long time, and not all proteins will reach their isoelectric point due to lack of time. This problem was solved many decades ago by using immobilizable ampholytes, which you will also use in the practical course. This was an ingenious idea. Essentially what was added to the amino acid derivatives was a polymerizable group. Maybe you recognize a bit of the acrylamide structure down here. You see the double bond that can be activated by radical polymerization and thus produce chains of immobilized ampholytes. Well, it's now hard to see if I just polymerize many ampholytes in a polyacrylamide gel, how this would generate a pH gradient. Let's look at that in a second. Making an immobilized pH gradient derives a little bit its technique from making a gradient in HPLC or in liquid chromatography in general. You have two solutions, one with a high pH buffer and one having a low pH buffer. Let's assume high pH is pH 10 and the low pH is pH 3. To the high pH buffer you add 20% sucrose or similar molecule that increases the density, while this is not done with the low pH buffer. Now as you start pumping, you start with the low pH buffer, and you have a valve that can be controlled by a kind of a computer, just like making a liquid chromatography gradient. So first of all, the low pH buffer is entering, but with time more and more of pump B is pumping, and the high pH buffer is underlaid under the low pH buffer. It's not only a buffer, but it also contains the acrylamide, obviously, for the polymerization. So as the gel liquid moves up between the glass plates, which are about 1 millimeter apart, the more dense solution will always stay at the bottom. That means the high pH will be at the bottom and the low pH will be at the top. If you do this carefully, avoiding turbulent flow, you will get a nice pH gradient with the low pH on the top and the high pH at the bottom. Now you can simply let the gel polymerize and the pH gradient will be immobilized. Here you see schematically in time how ampholytes form a pH gradient. On the top left, you see in the beginning there is no gradient at all, because the ampholytes are randomly distributed in solution. As you start the electric field, you turn on the voltage, ampholytes start to migrate, and after about 1.5 hours in this example, they have formed a pH gradient meaning they have all reached their own isoelectric point, and due to the somewhat broad band around that, they overlap and give a certain buffering capacity across the whole pH gradient range. Let's finish this part with the combination of isoelectric focusing and SDS-Page, a very powerful separation method for proteins which is still unrivaled today, although it was invented about 50 years ago. It's called two-dimensional gel electrophoresis. First, you put your sample on an isoelectric focusing gel and let it focus into bands, each protein at its isoelectric point. Then you take this gel strip, usually on a plastic backing, and you fix it on top of a polyacrylamide SDS-Page gel. Fixing is usually done with a bit of agarose. Then you migrate the proteins in the molecular weight separation dimension, and now you have a two-dimensional separation on the horizontal axis according to isoelectric point, on the vertical axis according to molecular weight. Since isoelectric point and molecular weight are not correlated at all in proteins, we speak about an orthogonal separation. That means the physical-chemical principles that separate proteins in each dimension are not correlated. As in other gels, you can choose the acrylamide concentrations to either separate somewhat larger proteins, as on the left side, or smaller proteins, as on the right side. Expert labs in the world can reach separations of more than 2,000 proteins in one two-dimensional polyacrylamide gel. The development of two-dimensional gel electrophoresis was also the start of the area of proteomics. This was the method of choice for separating proteins, and later on these proteins were identified by mass spectrometry. But in the beginning there was no mass spectrometry available before the development of multi- and electrospray ionization, so proteins were often plotted and identified, or at least assigned, using Western blots with antibodies. Let's close this chapter by looking at a two-dimensional gel electrophoresis analysis of a cancer cell line. You can see how many proteins are separated here in a pH gradient from 3 to 10 and over the molecular weight range on SDS-Page from 20,000 to 200,000. Each of these dark spots, which is stained with silver here, which is more sensitive than Coomassie, represents at least one protein. It can, however, not be excluded that there are multiple proteins migrating to the same spot, because there are so many proteins in a cell that even two-dimensional gel electrophoresis cannot always separate them all. There are also low abundance proteins in a cell which may not be visible on this gel, because there's not enough material there. You can see a lot of red crosses on this gel. This means that all these proteins were identified. If you would go to the web and click on the red cross, you would get to the protein identification and further on to more information about the protein. There are very few labs today that still do two-dimensional gel electrophoresis, thanks to advance of liquid chromatography mass spectrometry in proteomics. However, it should not be underestimated. It is still the most powerful protein separation technique available to date. Let's come to the summary of the electrophoresis part for protein separation. We heard about SDS-Page and isoelectric focusing. The chemistry of SDS-Page, how a polyacrylamide gel is made with its crosslinks by bisacrylamide, and the properties of SDS, sodium Dodecylsulfate. We introduced to you to the Ferguson plot, which shows that every protein has the same electrophoretic mobility in the presence of SDS in the absence of a polyacrylamide gel. This is really the basis of SDS-Page, because if proteins had different electrophoretic mobilities independent of their size, then the sizing mechanism would be overlaid by an electrophoretic separation mechanism based on charge. This would make interpretation of SDS-Page gels much more troublesome, as they would not be separated solely by size anymore. The Ferguson plot shows this at 0% T, where the electrophoretic mobility of all proteins is the same thanks to a constant surface charge density. Please recall the isoelectric point and how it can be derived and calculated from the number of charged amino acids in a protein. Remember also that this is an approximation, because this calculation does not take the three-dimensional structure and the charge distribution in proteins into account. Remember how to make an immobilized pH gradient, making a gradient gel and immobilizing the ampholytes. What is an immobilized ampholyte? What does it look like? And finally, the culmination by a combination of isoelectric focusing and SDS in 2D, two-dimensional gel electrophoresis, the basis of proteomics.